Okay, so now with what we learned in the previous video, we are ready to tackle more complicated circuits. So let's start with an example. Okay, let's say you have this circuit here. So for the first time, we have to deal with two capacitors. And what we have here is a circuit where, okay, there's a switch here. And we assume here that, well, we're told that the capacitors are initially on charge and we close the switch at t equals 0. So at t equals 0, you close the switch here. What will happen, obviously, is because we have a battery here, the charges will start to accumulate on the two capacitors. Okay, but this is not a simple charging circuit because we have two capacitors. Okay, and we have a resistance here. Now, we're given all the values to do the problem. The capacitance of the first capacitor here is 5 millifarad. That's 5 times 10 minus 3 farads. C2 is 6 millifarad. We know the EMF of the battery, 8 volts, and the resistance is 1.20 kilo ohms. Okay, so we have all the information about the circuit. And the question we are asked to answer is, what will be the charge on C1, on the first capacitor, 10 seconds after the switch is closed? Okay, so how do we start a problem like this? Now, you know this is a charging circuit, capacitors are charged, but you cannot apply the equations we've seen for charging a circuit directly in this circuit here, because all the equations we've seen for charging circuits apply to a simple circuit where there's only one capacitor and one resistor. So obviously what we need to do first is to combine those two capacitors which are in parallel. Okay, obviously here, and again, the rule for capacitors in parallel is the same rule as for resistors in parallel. You must be able to draw a closed loop that contains only those two capacitors and nothing else. No third capacitor, no resistors, no battery, nothing else. So after you close the switch here, clearly those two capacitors are in parallel. So we can combine them. And so that's what we'll do. We'll combine them into an equivalent capacitance. And remember the rule for two capacitors in parallel, the rule is that the equivalent capacitance is equal to the sum of C1 and C2. This is the rule we have seen for resistors in series, but the rules are flipped when we consider capacitors. So C equivalent would be equal to C1 plus C2. So we just add those two values here, and we get 11 millifarad. Okay, so what do we get? After combining the two capacitors here, we have an equivalent capacitor here, C equivalent. So I've combined the two. Okay, the EMF stays the same, resistance has not changed, and we have now an equivalent capacitance of 11 millifarad. Okay, 11 times 10 minus 3 farads. Now we have a circuit that we have dealt with before, that we have solved completely. We have only one capacitor, one resistor connected with the battery in series. So we know now that we can use the equations we've seen before for charging capacitors. Okay, the question was to find what's the charge on C1 10 seconds after we close the switch. So now we don't have C1 in this circuit anymore. It has been combined with C2 to get the equivalent capacitance. So what we can do here, well, actually now, because we have an equivalent circuit that we've solved, we can find everything about this circuit at any time. We can find the current, the charge on the capacitor, we can find the voltages across the resistor, the capacitor, everything at any time. But notice that when we calculate the time constant, we are working with the equivalent circuit here. So the time constant is R times C equivalent. So you have to use the C equivalent here in RC, and you get 13.2 seconds. That's the time constant. Now we can find, for example, the charge on this equivalent capacitor here, on this side here, at any time using this equation here. Notice we use again C equivalent because we're working with this equivalent circuit. So we have C equivalent in the equation here. Now, for example, if you want to find the charge on the equivalent capacitance at 10 seconds, then we know everything. We know C equivalent E tau, so we plug in T equal 10 seconds and we'll get 46.75 millicoulomb. that's 10 to the minus 3 coulombs. That's the charge on this side here, because the charges would be positive on this side of the capacitor here because of the positive battery here, positive polarity here, so I have plus and minus here. So what we found here, this is the charge on the positive plate here after 10 seconds. But this is not what we're looking for. We're looking for the charge on C1 after 10 seconds. So what we have to do now is that, so this number is not the final answer. We have to undo our step. We have to undo this capacitor here and go back to the two equivalent, the two capacitor initially that we combined, which were C1 and C2. C1 and C2 were in parallel. Now remember that when two capacitors are in parallel, they don't necessarily have the same charge on them, but they have the same voltage. So what we need to work with, actually this Q here will not be useful to us to find the final answer. We can't use that. What we have to work with is the voltage, because the voltage across C equivalent will be the same as the voltage across C1 and C2. So let's calculate the voltage. Well, the voltage at any time on a capacitor is just equal to the charge on that capacitor at that time divided by the capacitance. So the voltage across C equivalent is at 10 seconds is just the charge that we just found. Well, actually, we do use that charge at that step. So the charge that we just found here at 10 seconds, and we divide that by C equivalent, and that gives us the voltage across this capacitor here at 10 seconds, and it's 4.250 volts. Okay, now that we have the voltage here, we can undo our steps and go back to the original circuit. And what we get is, okay, so that was the original circuit, and now we found that this Q here is Q on the equivalent capacitor. Okay, that was this value here. The voltage on the equivalent capacitor we found was 4.25 volts. That's what we did before. Now, we use the fact that C1 and C2 are in parallel, so they both have the same voltage. They both have a voltage of 4.25 volts across them. Now we can find the charge on C1. Okay, by the way, this value here, all those values I'm talking about here, this value and this value here, everything is at 10 seconds, right? So to find the charge on C1 at 10 seconds, I can just go back to use the basic equation, which is the charge on any capacitor at a given time is equal to its capacitance times the voltage across it. So we know the voltage across C1 is 4.25 volts at 10 seconds, and you multiply by C1, which, if you recall, was equal to 5 millifarad. So you do that, 5 millifarad times this here, you get that value here. That's the final answer, and we're done. Okay, this is the charge on C1 at 10 seconds. Now, just to complete, again, as far as the question is concerned, we're done. But we can also find the charge on C2 at 10 seconds. Then we just use C2 times the voltage across C2, which is also 4.25 volts. And C2 was 6 millifarad. So if you do that, you get this. Okay. Now notice that the charge on C2 plus the charge on C1 gives the total charge on C equivalent, which is expected because all the charge that was moved by the battery ended up moving on C equivalent or on C1 and C2. So this charge here is equal to the sum of those two charges here. Okay, and we're done with this problem. By the way, here I wrote the values with 4 sig figs just to show that everything works perfectly, but of course we should round off to 3 sig figs for our final answer. So the final answer should be 21.3 millicoulomb on C1 at 10 seconds. Okay, so we've seen this is an example of a circuit that we had to combine. We had to combine capacitors before we could use the formula for the equivalent circuit of a charging RC circuit. Now, we can deal sometimes with more complex RC circuits. For example, here, this is not really clear, sorry, but the key point here is that you have a switch here, you have a battery here, you have 4 resistors, and then you have this capacitor here connected here. And let's say let's say that as before we close the switch at t equals 0, and let's say that the capacitor here is initially on charge. Let's say you ask the following question: what is the current out of the battery at 5 seconds. How would you answer that? Again, you can say, well, this is a charging circuit because this is the capacitor is initially on charge. You close the switch, so you know charges will start to accumulate on the capacitor. But before we can use any equation that we've seen before, we will have to simplify all of that here in in the form of just one resistor connected in series with the capacitor. So we'll have to combine all the resistors together here. But if you look at that for a second, you can't combine anything. Those two resistors are not in series. Those two resistors here are not in series. Those two resistors are not in parallel, because if you try to do a closed loop like this here, you don't have only those two resistors, you also have a capacitor. So those two are not in parallel. Actually, it's impossible in this circuit to combine any resistor. So we are stuck. We cannot simplify that. We cannot bring that to the form of a battery with one capacitor and one resistor all in series. We cannot. This means that that the formula we've seen before cannot be used to answer the question here, and we will need a more powerful approach to this circuit. Of course, there's a way to solve this circuit, but this is beyond the level of what we're going to cover this semester. So actually, this equation here, we cannot answer. There's no way to answer this question for this circuit with the knowledge we have gained so far. Another example of a question is, what's the charge, let's say, on the capacitor at 10 seconds? Again, impossible to answer. So for a more complicated circuit here where we cannot simplify, we cannot calculate anything at arbitrary times. That's the problem. Okay, the problem with those questions is that they're asking us to calculate something at some arbitrary value of time. We cannot answer those questions. In a circuit which cannot be replaced by an equivalent circuit with only one resistor and one capacitor, then it turns out we can only do the following. We can only calculate the properties of the circuit. By properties of the circuit, I mean the currents, the voltages, the charges, everything. We can only calculate the properties at two special values of time, at t equals 0 and at t equals infinity. So at the instant we close the switch and after you waited a very long time. Now in practice, you can never wait an infinite amount of time. So in practice, after you've waited the equivalent of about 7 times the time constant, so it depends. Usually it can be 30, 40 seconds. In some circuits, it can be a minute or two. But after a few minutes, usually things don't change much anymore, and it's for all practical purposes, you can consider t equal infinity to just be a few minutes. Okay. Now, how does that work? So here's the key principles. Here are the key principles. If you have a capacitor that is initially uncharged and you have a battery and you connect that to the capacitor and you have a bunch of resistors and capacitors and you cannot simplify, when the capacitor is initially uncharged, you can replace the capacitor by an ideal wire at t equals 0 only. Okay, so just at t equals 0, you can treat the capacitor as an ideal wire. At any other times, you cannot do that. So this trick here, replacing by an ideal wire, works only at t equals 0. And that's why we can solve at t equals 0, because we can use that trick. If the capacitor has an initial charge, Q initial, so when you close the switch, let's say there's already some charge on the capacitor, then just at that instant, what you can do is that you can, at t equals 0, that's when I close the switch, you can replace the capacitor by an ideal battery with EMF equal to QI over C. So you have your capacitor, you can basically treat your capacitor as a battery with an EMF QI over C. Okay. So that's just true at t equals 0. So you have your capacitor here, and let's say that this is a capacitor here, and let's say that is charged with a positive charge here, negative charge here, and with the value here equal to Q initial. At t equals 0, you can replace that by a battery. Okay, so this is now a symbol for a battery here with an EMF equal to QI over C. So you can replace this by this only at t equals 0. Okay, that's for the capacitor that is has an initial charge Qi. Now, what about t equal infinity? So the trick is that at t equal infinity, capacitors become fully charged. So they reach the maximum charge. We don't know the value at the maximum charges. We can calculate it later, but for now we just know that they are fully charged. And what's special is that when they're fully charged, now no charges can be added to their place, so they block all the currents in their branches. They don't block the currents everywhere in the circuit, they just block the currents in their branches. So at T1 infinity, no current can flow in only in the branches containing capacitors at T equal infinity. So basically the branches that contain capacitors you can be replaced by an open switch, an open circuit. It blocks, no current can flow there. Okay, so when you can, at T equal infinity, you can basically remove all the branches containing the capacitors because no currents can flow there. So for example, if we go back to this circuit and you can ask the following questions, I'm not going to solve them, I'm just going to leave them as open questions. And you should try them, and that will be one problem, that practice problem for you to do. So in this circuit, what is the current flowing out of the battery? So clearly, it would be a current flowing like this here, but the value of the current here changes with time. So the question is, what is the current flowing here at t equals 0 and at t equals infinity? The key point is that at t equals 0, you can replace, remember this capacitor was initially uncharged. So at t equals 0 for this circuit, you can replace this part here, this capacitor, by a wire. And then you can find the current here by combining resistors. At t equals infinity, this capacitor is fully charged and it will block all currents. So you can remove this branch here and you can calculate again the current flowing out of the battery, which would be a different value. You can also calculate the following, answer the following question. What's the current flowing in the branch of the capacitor? So in this branch here, what's the current flowing here at t equals 0 and at t equals infinity? At t equals 0, it requires some work. You have to solve the circuit and find the current here. At t equals infinity, the answer is obvious. At t equals infinity, the capacitor here is fully charged. So in this branch here, there's no current. So the answer is that at t equals infinity, the current flowing in the branch of the capacitor is equal to 0. But at t equals 0, you have to do some work for that. What's the charge on the capacitor at t equals 0 and at t equals infinity? Again, there's one case which is obvious. At t equals 0, we started uncharged. So there's no charge on the capacitor at t equals 0. At t equals infinity, it would be charged. So even though at t equals infinity, we said there's no current flowing here, but there's a charge on the capacitor here, right? And then to find that, well, I'll let you try it and we'll discuss it in class a bit later. Okay, so that's all we're going to see for RC circuits for now. We're going to move on to a new type of circuit element in the next lecture. Thank you.